Good morning, everyone. Thank you very much you are present here. Today, the Professor Kushi and to present the seminar on fractional calculus, talk about K-Psi, Hilfer fractional derivative and the associated differential equations. The Professor Kisher is work Department of Mathematics, Shivai University, India. And the Professor Kisher Kush, you have 1 hour talk about your work. Okay, thank you, everybody. The Professor Kisher, you have 1 hour.
Okay, can I start now, Jose?
Okay.
Hello? May I start now?
Yes, you pass this in this PDF in copy.
Okay, so I'm starting, Jose. Thank you.
Okay, thank you.
Okay, then. Firstly, good morning, one and all. I thank organizing committee of the university for giving me an opportunity to talk in this seminar on fractional calculus. This is the outline of my talk. Firstly, we will discuss the necessity of generalized fractional derivative. Then we will discuss the definition of K-Psi Hilfer derivative. Then weighted space is required to study the property of K-Psi Riemann level derivative and K-Psi Hilfer derivative. So we have to fix the weighted space. Then we will discuss the relation between K-Psi Riemann level derivative and K-Psi Riemann level integral. Later on, we will discuss the properties of K-Psi Hilfer fractional derivative, and then we will study K-Psi Hilfer fractional differential equation, and lastly, we will discuss conclusion. This presentation is based on the paper which is written with my student A.D. Mai on the nonlinear K-Psi Hilfer differential equation, which is published in Chaos, Solidus, and Fractals in 2021. We know the history of fractional calculus goes back to the 17th century. The idea has arisen from the discussion between Leibniz and L'Hopital, these two mathematicians, and the discussion was about classical derivative, where about nth order derivative, and question was discussed what will happen when n is equal to half. Okay, so this was we are considering the birth of fractional calculus, and since then there are many different definitions of fractional derivative, and we can say that this definition generally do not coincide with each other. Possibly it is due to the fact that different authors try to preserve different properties of the classical integer order derivative. Now, when we observe the literature, generally a new fractional derivative is proposed with the two aims. First aim is the existing fractional derivative doesn't fulfill the properties of the classical ordinary derivative. Hence, someone is going for defining new derivative, or when one cannot demonstrate some physical process with the existing fractional derivative. At that time, also researchers are going to finding the new derivative, fractional derivative. Now, whenever we are defining new derivative, uh, and new derivative is defined, it is generally expected that that fractional derivative must satisfy this property which classical derivative bears. First property is classical compatible, backward compatibility. Whenever fractional derivative is defined, and if that order, real order, if you are replacing by integer order, it must give your classical derivative. Zeroth order derivative must give your function as it is. For that fractional derivative, linearity property should be there. That fractional derivative must satisfy commutation property. Index law must be there. We must able to define product rule for that fractional derivative, and we must able to give the chain rule for that. Okay. Uh, Number of definitions we can see in literature more than 25 plus definitions, near about 30 definitions we can see related to your fractional differentiation in literature. Among all these fractional derivative, most widely used definitions are Riemann level fractional derivative and classical, that is your Caputo fractional derivative. We know Riemann level fractional derivative plays important role mainly in the development of theory of fractional derivative, and in application related to the pure mathematics, while applied problem require a proper definition of fractional derivative which can provide initial condition with physical interpretation, and this makes the Caputo fractional derivative more suitable to apply. Now, as already I have discussed, there are a number of definition of fractional derivatives and integral, and many author defining different type of fractional derivative, and it may happen that in future many definitions may come. Okay, so it is necessary to unify this definition so that we can study the theory of fractional derivative under one roof, having generalized derivative with us. The first attempt toward the generalization of fractional order derivative, sorry, or here is power cut. Okay, so okay, so first attempt toward the generalization of fractional derivative operator have been made by Hilfer in 2000, who introduced fractional derivative of two parameter. Okay, this is the definition which we know. This is Hilfer fractional derivative of two parameter, and we know it interpolate between your Riemann-Leibel fractional derivative and the Caputo fractional derivative for alpha between two consecutive natural number n minus 1 to n, and beta between 0 to 1 including 0 and 1. This derivative is Riemann-Leibel fractional integral of order beta into n minus alpha operated on n time classical derivative operator on this fractional integral, Riemann-Leibel fractional integral of order 1 minus beta n minus alpha. Okay, and when we are putting beta is equal to 0, at that time we are getting Riemann-Leibel derivative, and when beta is equal to 1, it gives your Caputo fractional derivative. Okay. Then concept of fractional derivative of the function f with respect to another function psi, in the sense of Riemann-Leibel, uh, have been appeared in the monograph of Kilbas, and we call it psi Riemann-Leibel fractional derivative. Sorry, psi Riemann-Leibel fractional integral. This is the definition of psi Riemann-Leibel fractional integral, and this is the definition of psi Riemann-Leibel fractional derivative. For that, we require psi is increasing positive monotone function on the closed interval, which has a continuous derivative. Okay, so that this fractional integral is exist. Having definition of fractional integral in the sense of they with respect to another function psi, we have the definition of Riemann-Leibel derivative with respect to the function psi. This is the definition. Okay. Motivated by the definition of psi Riemann-Leibel derivative, Almeida in 2017 introduced the concept of fractional derivative of the function f with respect to another function psi in the sense of Caputo. Okay, so this is the definition of Caputo derivative, which we know. Okay, this is in the sense of Caputo. Caputo derivative with respect to other functions. In 2018, Souza and Oliver have introduced generalized version of Hilbert derivative, which is called a psi-Hilbert fractional derivative. Okay, so when alpha is between two consecutive natural number, and when f is n time continuously differentiable function and psi is n time continuously differentiable function, derivative is not vanishing, then psi-Hilbert derivative of function with respect to of order alpha and of type beta, beta is between 0 to 1, it is defined in this sense. In this interesting work, it is proved that psi-Hilbert fractional derivative includes wide class of fractional derivatives, and numerous definition of fractional derivative can be obtained by choosing the function psi and taking particular values of beta. Okay. In 2007, Diaz and Pereguin in 9 introduced this K gamma function. Okay, so it is generalization of Euler gamma function. When z is complex number whose real part is greater than 0, k is positive real number. Uh, Having this with us, this is the definition of K gamma function, which is generalization of Euler gamma function. When we assume k is approaching to 0, at that time this gamma k z approaches to gamma z. Okay, so if you are putting k equal to 1, it converted in the form of Euler gamma function. Okay, now we have seen a number of definitions of fractional derivative are given in the term of fractional integral, and we know the definition of fractional integral has depends upon the Euler gamma function. And since k gamma function is the natural generalization of Euler gamma function, it is natural to expect the kind of fractional derivative and fractional integral with additional parameter. Motivated by this concept, uh, okay, this is the definition of K gamma function, which already I have discussed. Okay, these are the few property which need to develop the calculus of K psi Hilbert derivative. This is functional property of K gamma function. Okay, and gamma K of K, it is 1, and this is the relation between Euler gamma function and K gamma function. Okay. And this is the k beta function, which is generalization of beta function, and this is the relation between k beta function and k gamma function. Similar type of relation we are getting as in Euler gamma function and beta function. Motivated by the concept of k gamma function, in 10, k Riemann level fractional integral is defined when h is integrable function defined on closed interval ab, alpha and k are positive real number, then k Riemann level fractional integral of order alpha is defined in this sense. Okay. So additionally here we can see that here k is applied, gamma k is applied, and here is alpha by k. If you are putting k is equal to 1 here, it is converted to your classical Riemann-Leibniz fractional integral. Having this definition in 11, k Riemann-Leibniz fractional derivative is defined in this sense. Okay, it is when k and alpha positive real number and m is ceiling of alpha by k, h is integrable function, then k Riemann fractional derivative of h of order alpha is defined in this way. So it is m time operator k by k into d by dot d tau operated on k Riemann level fractional integral of order mk minus alpha. Motivated by this concept, having definition of k Riemann level fractional integral in 12, the concept of K-Psi Riemann level fractional integration is defined, and they have studied few properties related to it. Okay, so this is the definition of Riemann level k Riemann level derivative with respect to another function. Okay, so we are taking that function with respect to psi here. Motivated by this study, okay, having with us k Riemann level derivative, k Riemann level fractional integral, and k psi Riemann level fractional integral, this definition, okay, and the concept of psi Hilfer derivative, that is given by Jose and Souza and Oliveira. We attempted to give a generalized version of Hilbert derivative with additional parameter k, and we have tried to define a new derivative, okay, which we cannot call directly it is a new derivative. It is generalized version of Hilbert derivative, which also generalize our existing psi Hilbert derivative, which contain an additional parameter k, and we have given the name to this derivative as k psi Hilbert derivative. Okay, so if we are considering alpha k positive real number, beta is number between 0 to 1, m is ceiling of this division alpha by k, psi is m time continuously differentiable function, its derivative is non-vanishing on closed interval ab, h is m time continuously differentiable function. Okay, then k psi Hilbert fractional derivative of this function h of order alpha and type beta is defined in this way. This is k psi Riemann level derivative of order m beta into mk minus alpha, which is operated on m time operator k upon psi dash tau d by d tau, which is operated on this k psi Riemann level fractional integral of order 1 minus beta mk minus alpha. The main difficulty we faced while defining this derivative, to place the parameter k at the appropriate place, so that the derivative definition must be well defined, and if we take k is equal to 1, it must give your psi Hilbert derivative, and it must contain include all other derivative as a particular cases. Okay, so uh, putting k at the appropriate place, that was the main difficulty while defining this derivative. Okay, but we got success while defining this definition. We observed when we are putting beta is equal to 0, this K-psi Hilbert derivative which we defined is converted in the form of K-psi Riemann fractional integral. If you put here psi t is equal to t, it is converted to k Riemann fractional derivative, and if you are taking k is equal to 1, it is again converted to your Riemann derivative. If you are taking beta is equal to 1, this k-psi Hilbert derivative reduces to k-psi Caputo derivative, which is given here, and if you again take psi t is equal to t, it is converted to what your k Caputo derivative, and if you are again taking k is equal to 1 here, it is converted to your our classical Caputo derivative. Now, if you are taking k is equal to 1 here, this k psi Hilbert derivative is converted in the form of psi Hilbert derivative, which was introduced by um, Souza and Oliveira. And for psi t is equal to 2 and k is equal to 1, this derivative is reduced to your Hilfer fractional derivative, which was introduced by Hilfer, okay, and studied in the paper of Furati. Now, when we put here psi t is equal to t in this definition is reduced to what your K Hilbert fractional derivative. Okay. In literature, some author in 13 have tried to give the definition of Hilbert derivative, but what we observe that it does not include the famous derivative, Riemann-Leibniz derivative and K-Riemann-Leibniz derivative. Okay, but the attempt which we have made to define K-Hilfer derivative, okay, after defining it, we observed that when we put psi t is equal to t, it converted in this form, and it reduces when we take beta is equal to 0. It reduces in the form of K Riemann-Leibniz derivative. Okay, so it act real generalization of or different type of derivative. Okay, so this is the table which we have tried to give here. Okay, so for k greater than 0, and for different values of beta and different values of psi, here we are getting different type of k derivatives here. K-Psi Riemann derivative, K-Psi Caputo derivative, K-Hilbert derivative. So these are the list, but this is not the exhaustive list. Okay, so many derivative we can write in terms of K derivative. Okay, and for K is equal to 1, we are getting all the derivatives here, which are mentioned in the paper of Souza and Oliveira. Okay, so because for K equal to 1, already I have discussed that this K-Hilbert derivative, K-Psi Hilbert derivative is converted in the form of Psi Hilbert derivative. Okay, now to study the property of K-Hilfer derivative and its particular cases, K-Psi Riemann-Leibniz derivative and K-Psi Riemann-Leibniz fractional integral, we require an appropriate space. Okay, so for alpha k between 0 to infinity, considering alpha is less than k, beta between 0 to 1, we have defined this number psi zeta k, which is alpha plus beta into k minus alpha, and we have considered this weighted space, which is defined on the line of this paper 7, which is the paper of again Souza and Oliveira. Okay, so the basic paper we have referred this to define this weighted space. Okay, and we can check that this zeta k upon k lies between 0 to 1. Okay, and this is a non-linear space with this norm, maximum norm, supremum norm, we can call it. Okay, and we also require this space, this weighted space, to study some properties related to K-Psi derivative. Okay, so having K-Psi Hilbert derivative with us, to develop the calculus of K-Psi Hilbert derivative, firstly we have to develop few properties of K-Psi Riemann-Leibniz fractional integral and K-Psi Riemann-Leibniz fractional derivative. We have to produce few results uh, giving the relation between K-Psi Riemann-Leibniz fractional integral and derivative. Okay, so firstly we will discuss few properties which we have proved in that paper. This is the first property which we have proved. When mu and k is positive number between 0 to infinity, this K-Psi Riemann-Leibniz fractional integral can be written as psi Riemann-Leibniz fractional integral with this parameter in multiplication. This K-Psi Riemann-Leibniz fractional integral satisfies semi-group property. Okay, and if we are considering the order of K-Psi Riemann-Leibniz fractional integral mu between these two parameter omega and k, where omega and k are positive real number, and if you are considering h in this weighted space, okay, with suffix omega by k, then the K-Psi Riemann-Leibniz fractional integral of order mu, when we take t tending to a in uh, considering positive side limit, it gives 0. So it is justifiable to put that the value of this fractional integral at a is equal to 0. Okay, so which is applicable for proving equivalent fractional integral equation to the fractional differential equation involving K-Hilfer derivative. Okay, these are few properties which we have proved. We will call these are the mapping property for the K-Psi Riemann-Leibniz fractional integral. If you are considering mu is positive real number, okay, so then this K-Psi Riemann-Leibniz maps the continuous space define on closed interval AB to continuous space on closed interval AB. If we are considering two real number omega and k, satisfying this condition 0 less than or equal to omega less than k, and if d is the number between two number a and b, if g lies in this weighted space from a to d, and g lies in the continuous space from d to b, okay, where d is between a to b, then this g lies in the weighted space from a to b, okay. This is another mapping property of K-Psi Riemann-Leibel fractional integral. If mu, omega, k are positive real number, mu is between omega and k, then this K-Psi Riemann-Leibel fractional integral operator is bounded from this weighted operator, weighted space, to the space of continuous function defined on closed AB. And for any function in this weighted space, this is the boundedness condition. Okay. This is the boundedness of the mapping from weighted space to weighted space. If again mu, omega, k are positive real number, omega is less than k, this case high Riemann fractional integral is bounded from this weighted space to this weighted space, and it satisfies this boundedness condition. These all properties we have used to prove the equivalent fractional integral equation to the fractional differential equation involving K-Psi Hilfer fractional derivative. Again, on the similar line of the Article 7 of Jose and Oliveira, we have given the formula for power function, fractional integral of this power function, okay, which is generalization of fractional integral of power function when we are taking k is equal to 1. Again, we are arising to the case of psi Riemann fractional integral of the power function. Okay, so we can see here, if we are taking here k equal to 1, psi t is equal to 1, this theorem 20 reduces in this form, which result proved in your book of Podlinese, Kaidithelm, or the monograph by Kilbas and other authors. Now, again, to deal with the calculus of K-Psi Hilfer derivative, we need to discuss the properties of K-Psi Hilfer derivative and K-Psi Riemann integral, the relation between it. Okay. So, firstly, we have proved this simple property. It's a m time operator, 1 upon psi dash t d by dt operated on m time integration. It gives h of t when m is natural number and k is positive real number for the continuous function. Similar type of property is also satisfied by this K-Psi Riemann-Leibel fractional integral. Okay, where m we are assuming here natural number. Okay, and this property we have utilized to prove this theorem 22. Okay, so if I am taking alpha k are positive real number, m is ceiling of this division alpha by k, and h is in this space, weighted space, then K-Psi Riemann-Leibel derivative of K-Psi Riemann-Leibel fractional integral of this function h of t is equal to h of t. This we are obtaining. Again, this theorem says that we can write K-Psi Riemann-Leibel derivative in terms of psi Riemann-Leibel derivative with this parameter in multiplication k raised to alpha by k. Okay, for continuous function h defined on closed interval AB. This is the relation between integration and derivative. So it is K-Psi Riemann-Leibel integral of K-Psi Riemann-Leibel derivative. Okay, so this formula is generated. Okay, of course we are considering here alpha k sigma are positive, sigma is less than k, and m is ceiling of this, and h we are considering in this weighted space. Okay. Now, after taking psi t is equal to t in this and k is equal to 1, we have observed that this theorem is converted in this format. Okay, and which is the standard result which we can see in any type of any book which are related to fractional differential equation, say research monograph by say Kai Dithelm, or research monograph by Kilbas and other authors. So we are obtaining this result as the particular case of this result. Now, this property we require to develop the calculus of K-Psi Hilfer derivative. Okay, so this property says that your K-Psi Riemann level derivative can be written as K-Psi Riemann level derivative of this fractional integral. Okay, where this gamma k is this number alpha plus beta k minus alpha, alpha less than k. Okay, so this property again we need to develop the calculus. Okay, now, these are the properties related to K-Psi-Hilbert derivative. So first, this property says that your K-Psi-Hilbert derivative is written in terms of Psi-Hilbert derivative of order alpha by k with this additional parameter here k raised to alpha by k. Okay, there is a derivative for the power function when this zeta xi by k must be greater than minus 1. Okay, and we know that if you are able to give the formula for the derivative of power function, we can develop the exponential function as well as trigonometry function, because exponential function and trigonometry function sine cos and so on, they have power series convergent power series expansion. So we can write derivative of sum is equal to sum of derivative in the infinite series. Okay, so we can generate the derivative of exponential function and trigonometric function using this formula. Uh, this is the result related with K-Psi Riemann level integral of K-Psi Hilbert derivative. Okay. So when alpha k are positive, alpha is less than k, beta is between 0 to k, psi k is this number, then K-Psi Riemann level fractional integral of K-Psi Hilbert derivative is written in this format. This is K-Psi Riemann level fractional integral of RL derivative. We can see here this order is same here, which is zeta k. Okay, and this is the most important property which we have utilized to derive the equivalent fractional integral equation for the fractional differential equation involving K-Psi Hilbert derivative. And of course this is true for this h is in this weighted space of order zeta k. And this is also one of the property when h is integrable function, and this derivative k real derivative is exist for this function h. Then this is the relation between derivative and integration. Derivative of integration is written in this format. Again, this is given in terms of Riemann level derivative. So this is Hilbert derivative of fractional integral. We can write uh, k psi Riemann level fractional integral of k Riemann level derivative, and we can see here order is same again. Okay, so this relation Hilbert derivative of integration we have written in the form of k psi Riemann level integral of this K-Psi Riemann level derivative. Okay, having this calculus part with us, we have proved the existence and uniqueness of solution for K-Psi Hilbert fractional differential equations. We have considered this nonlinear differential equation in 5 and 6. Okay, with this initial condition involving this fractional integral. Okay, and assuming alpha k alpha less than k, both are positive real number, beta is between 0 to 1, psi k is this number, alpha plus beta into k minus alpha. We assume that f is continuous function. Okay, and we are assumed that this function lies in this weighted space whenever y lies in this weighted space. Okay, then y satisfies this differential initial value problem 5 and 6 if and only if it is the solution of this fractional integral equation. Okay, so whatever the result we have proved for K-Psi Hilbert derivative, K-Psi Riemann level derivative, and K-Psi Riemann level fractional integral. Okay, that result we have utilized to prove this result. Okay, so of course we have not I am not presenting here the outline of the proof. Okay, and when we put here in this result k equal to 1, psi t is equal to k equal to 1, uh, this result is converted in the form of the result which we have given by Souza and Olivera. And when we are taking psi t and k is equal to 1, this result include the result of chi d 3, and this this related to what your equivalent fractional integral equation of nonlinear fractional differential equation. Okay, and we have given here existence theorem using Banach contraction principle. Okay, so simple existence result we have given here, existence and uniqueness result. Okay, so assuming the same type of assumption in the previous theorem 30, f we have considered in this weighted space whenever y is in this weighted space. Okay, and f satisfies the ellipsis condition in second argument. Okay, then there is a unique solution for this problem, K-Psi Hilfer derivative 5 and 6. Okay, so final conclusion is that we have attempted to give a generalized version of Hilfer derivative, which we have given the name K-Psi Hilfer derivative. Okay, uh, this is the definition which we have introduced. Okay, and we have observed that for different values of different functions psi and different parameter beta and k, this K-Psi Hilfer derivative produces different type of derivative, fractional derivative. Okay, and that are recorded in the table. Of course, that the table which we have given, that does not contain the exhaustive list of the derivative. We have demonstrated few properties of K-Psi Riemann fractional integral and derivative that are required to build up the calculus of K-Psi Hilfer fractional derivative operator, and we have developed for the calculus of K-Psi Hilfer derivative operator and derived the equivalent fractional integral to nonlinear K-Psi Hilfer fractional differential equation. So this is the conclusion. If these are the references which have, so some of the references we have mentioned here. Okay, that basic paper which we have used to develop the theory of this paper. Thank you.
Hi.
Uh,
Thank,
hi,
thank,
hi,
thank
Joseph.
you. Thank
Yes,
you. Thank
thank
you
you,
very
Joseph.
much. Thank you. And the one question, the professor Felix Silva, is there the fundamental theorem of the calculus consider PC Hilfer, K-Psi Hilfer fractional derivative? The first question.
Is there the fundamental of calculus considering K-Psi Hilbert derivative? Okay, sir. Yes. Um, we, the results which we have proved in this theorem, means in this paper. Okay, just 1 year we have proved. Okay, and later on we have not done any work related to it, and we have not considered this property. Okay, so we have not given a theorem related to the fundamental theorem of calculus related to K-Psi Hilbert derivative. Okay, it may be a problem for other researcher, or we will try this problem in future.
Another question. Another question. Um, and the live role. And the, for example, you in 2018 years, and I and the professor Edmundo Capelas to propose a new fractional operator, to call fractional derivative. And the past the time, the another research put the K in this example, this work. And it's in 2099, I realized a new work talk about the using the Hill fractional derivative to libraries road type 1 and type 2. In this moment, it's very important, these questions. Is it possible to realize the libraries really the K-Psi fractional derivative?
Yes, yes. Already I have discussed, when we are giving any type of definition related to fractional derivative, generally we are trying for this type of properties, this type of properties. Okay, but we have not tried for Leibniz rule in the sense of this K-Psi Hilfer derivative. Okay, what is the main difficulty which we are facing, or any researcher who has defined this fractional derivative? Okay, main difficulty is what when we are considering classical derivative, n time classical derivative, f into g, it's Leibniz rule we are getting in this format. Okay, and we can
Okay.
interchange the order of f and g here, so this f and g I can write g into f, so that it generate the same type of formula. If I am using the commutativity of product f into g, I can write g into f here. But you go for the Leibniz rule, which is defined for Riemann-Leibniz derivative as well as Caputo derivative. We cannot commute the order of f and g. So when we are defined the formula for f into g, we cannot write it does not generate the same type of formula for g into f in the case of Riemann-Leibniz derivative also, as well as in the case of Caputo derivative also. You can take simple example, f of t is equal to t, g of t is equal to t. Okay, in case of Riemann-Leibniz derivative, here we are getting some classical derivative, and here we are getting some fractional derivative, and we know that classical derivative does not equal to your fractional derivative when we are taking real order. Okay, so this is the main difficulty when we are considering the Leibniz rule for fractional derivative. Okay, uh, Jose and Oliveira has attempted this problem in their derivative when they have considered this problem related to K-Psi, Hilfer derivative, Psi-Hilfer derivative. Okay, they have attempted. Okay, I have seen that work also, and but the main difficulty which I am, in my sense, main difficulty while defining the Leibniz rule, we cannot change the order of the function f into g. We cannot write if you are given the formula for f into g, the same formula cannot work for the g into f. Miss the same result is not obtained for g into f. Okay, that is my observation. Okay, that's why I have not attempted that question to define the K-Psi, Leibniz rule for the K-Psi Hilfer derivative.
Okay. And I have a question. Two questions. And the first question is about the next step you are this work. For example, you have the continuous talk about the fractional differential equations about this K-Psi Hilfer fraction derivative, for example.
I have not got question here, Jose. Please, can you repeat your question? Can you repeat your question, please?
For example, this work you talk about the K-Psi fraction derivative, okay? And the
Yes,
in
yes,
the next yes next step you have a new idea about the fractional differential equations or no?
No,
For
I am not
example,
getting. I
usually
am not getting your
the
question.
yes,
I am not getting your question
for,
properly, Jose. Can you type? Can
yeah,
you type so that I can understand the question?
for, for example, usually the multi solutions you about the existence, Unix, the multiplicity the solutions the using the fixed point theorem. You have your
Yes, yes.
idea and yeah. And okay, and okay, Professor Kishikushi, thank you, thank you very much. You present this work in the divulgation you work in here Brazil and another people to to work you, especially your students. Thank you, thank you very very much.
Thank you very much. Thank you for giving me an opportunity to talk all those people who are working in the field of fractional differential equation, and because of you, I am connecting with the peoples in Brazil. Okay, thank you very much.
Thank you.
Thank you, sir.
Obrigado, pessoal. Até uma próxima. Encerramos aqui o seminário, né? Mais um seminário de cálculo fracionário. O próximo seminário aí nós vamos divulgar, né? Em breve, já com as pessoas aqui do Brasil e pessoas de fora, né? Hoje nós tivemos a presença do professor Kust, né, da Índia, e falar um pouco sobre o trabalho que ele vem realizando com seus alunos. Professor Kish, thank you very much. In this moment, we finish the fractional calculus seminar. Okay? Thank you.
Thank you.
Bye bye.